Hello, I'm Erik Andersen from the University of Utah Department of Mechanical Engineering, here to present our work on design, modeling, and analysis of inductive resonant coupling wireless power transfer for microaerial vehicles. Microaerial vehicles, or MAVs, are incredibly useful tools whose utilization is limited by its flight time. Typical flight times for MAVs are just 20 to 30 minutes. Wirelessly powering MAVs is a potential solution to this problem. A wirelessly powered MAV will be able to operate for an extended period of time beyond the current 20 to 30 minutes. Additionally, it will allow the MAV to operate in hazardous environments when physically touching and changing the MAV's batteries could be unsafe. Our Resonant inductive wireless power transfer system is comprised of an RF frequency power amplifier, an L matching network for impedance matching, two planar Archimedes spiral coils, an AC-DC harmonic rectifier, and a DC-DC converter. In order to model this system, we reduce it to an equivalent circuit model using a two-port network. The goal of the modeling process is to maximize the figure of merit, gamma, which is defined as power required for the MAV to hover over the power inputted in the system. The reason we use this and not efficiency is because of the MAV dynamics. For every gram added to the weight of the received coil, the MAV needs more power to lift its own weight. Therefore, a lighter coil may not be as efficient as a heavier coil, but it will require the MAV to consume less power, making it easier for it to hover. This modeling gave us plots of gamma versus several other design factors. A gamma of 1 is required for the MAV to hover. Based on the modeling results, we built a receive coil to have 2 turns, 1.29 mm wire, 130 mm outer diameter, and a 1 mm pitch. Additionally, a sensing and control system is proposed that will enable the MAV to locate the optimal location to receive power, that being the center of the transmit coil. A high-frequency magnetic field induction coil sensor is designed that can measure the magnetic flux, and using the combination of 4 of these sensors, the MAV can locate its position relative to the center of the transmit coil. Then using a PID controller, the MAV can be driven to the center of the transmit coil. Here are some experimental results. For the 13.7 centimeter diameter 2-turn coil, the difference between the theoretical and experimental power received was 10.65%. For the 15.3 4-turn coil, the difference between the theoretical and experimental was larger, around 50%. This showed us that by using the lower turn coil, it would be possible for the MAV to receive enough power to hover. This is a demonstration of the MAV hovering using wireless power transfer. The MAV's position is being controlled through a custom ROS control loop using IRI motion capture cameras. It hovers at around 120 to 150 millimeters above the transmit coil for 8 seconds before landing. Thank you, and please come to the interactive session to learn more.